Hey there, everybody. We're going to be looking at an AP Physics C problem today, but we're going to be looking at it a little bit different. In the year 2020, so if you're viewing this like 18 years from now, this won't apply to you. But in the year 2020, we've got the Corona-19 thing going on, and as a result, the AP Physics C tests have kind of been drastically changed from what they used to be. Instead of having to kind of like grind out a bunch of math problems, we're going to have to describe stuff a lot more than normal. And as a result, what we're going to do is we're going to get some practice of looking at AP Physics C type problems, but thinking about how we would respond on kind of a text-based computer type of thing. So what we're doing here is we're looking at the 2019 AP Physics C Electricity and Magnetism for response question. And we're going to focus on question number 1 because I think it's set up in a way that we might see this year in kind of a scaffolded, like work your way through the problem. So let's go ahead and read through this question and just kind of talk about it because that's really what we're going to have to do this year. Whenever we're answering these questions, we're going to have to talk about our thoughts. So what we have is a very long, so an infinite length, thin, non-conducting cylinder, well, I guess not infinite, but it is very, very long, of length L. And it's centered on the y-axis as shown above. It's got a uniform linear charge density, and point P is located at the y-axis at some height C. And L is much, much greater than C here. Just thinking about this year, the first thing here is asking us to draw an arrow. We're probably not going to draw anything this year. How are you going to draw on the screen? How are you going to select and drag stuff? The College Board isn't designing new software for a month from now. But if we did, it would go up here. The left and right would cancel out due to symmetry, but we're not going to see a drawing problem more than likely. But what we will have is something like this. Describe the shape and location of the Gaussian surface that can be used to determine the electric field at point P due to the long similar. This is right up our alley. We know we're going to see a Gauss's law problem. It's almost a guarantee. But how they're going to ask the question about it might be like this. So if we're describing the shape, if we have a long cylinder here, we want to use a cylinder for our Gaussian surface, and that cylinder wants to be coaxial to this, so it kind of wants to wrap around it in the same line. So that's how we can describe it. For the next part here, we need to derive an expression. We're probably not going to do that this year. Maybe they'll ask us like which of these 4 is correct, but we're probably not going to have to actually math out ourselves something like this. We'll see something kind of about this later on though. Okay, so really the coaxial surface of the cylinder is what we want. If we go on to the next part of this problem, what we have now is that a proton has been released from rest at that point P, and on the axis below we're asked to sketch a velocity function and an acceleration function, which we probably won't be sketching, but maybe we'll see 3 or 4 different graphs and we have to pick one that's correct and then describe why it's correct. So the graph we're looking for, if we kind of think about this, we've got the infinite positive line of charge here, and then our proton is here, so it's going to be pushed away. We can think about that initial push as being the largest push because we're closest and the electric fields are pointing out. So the initial acceleration should be large, and it has to start here at point C. And then as it moves away, this acceleration will die off. If we go to the velocity, we're starting at rest, and since that initial push is large, we're going to increase the velocity quickly, but then kind of flatten out. So it'll kind of go up and then flatten out. The acceleration will come down quickly and then flatten out at 0 when it's an infinite distance away. But we're just kind of describing why that happened. The force from that, the electric field gets weaker and weaker, so the force is weaker and weaker as it moves away, so the acceleration drops. The velocity increased quickly due to the large acceleration, and then as the acceleration came closer and closer to 0, the velocity reached some terminal velocity. Just a quick little description. Now what we have is the original cylinder, the original charged cylinder of length L, is now replaced with a much shorter, thin, non-conducting cylinder, still not conducting, with the same uniform linear charge density, lambda. We have, it looks like a larger amount to the left, some length B, and on the right, a smaller amount, some length A. Once again, drawing an arrow, probably won't have to do, but if we had to select one, since there's more from this B side, there's going to be more electric field kind of pushing this way than there is this way due to the non-symmetry of the problem. So it's not going to just be up anymore. We're kind of pushing off to the right like this because we've got more stuff on the left here kind of pushing in this line. Is there a single Gaussian surface that can be used with Gauss's law to derive an expression for the electric field? Yes or no? We're probably going to see a lot of yes no's this year, just because you can like pick one and then give a reason to your answer. In this case, there is not a nice Gaussian surface. If you think about Gauss's law, it is the closed path integral, or the closed surface area integral of the electric field dotted with the dA vector, that area vector of your Gaussian surface. And that equals the charge enclosed over epsilon naught. We assume for Gauss's law, though, that the electric field is a constant. So it is the same radial distance away at every point. In this case, this left edge here over at B, that's a much farther radial distance of R than it is everywhere else along this. It's not symmetric on the other side. So we can't really use Gauss's law in this case. So the answer is a no. There's no symmetry there, so we can't use it like that. The radial distance is changing, and that's just a valid explanation of what's going on. If we were to try to solve this in our last part here, a student, whoever that could be, is arguing that we could use this integral in order to determine the electric field, which is absolutely right. An electric field is just some charge amount, well, kq over r squared, right? Where 1 over 4 pi epsilon naught is k, dq could be some charge amount, and then r squared could be a distance. And they're saying, look, if I take all the tiny bits of charge and I integrate them, I add them all up, I'll get the electric field. But we're going to have both a horizontal component, because this is at an angle, and a vertical component. So they're saying I can use this idea to write these two integrals. And they're asking me, one of the two expressions, one of these two integrals, the horizontal or the vertical, is not correct. One of these is wrong. Which one is it? So they're not asking you to write out this integral on the screen, but you're probably going to be writing this integral off on your sheet of paper. What we can see, and let's take a look real quick at this integral. Let's pull something around real quick. If we take a look at like what this integral is kind of saying here, let's get the glove on, pushing, because this might be what you have to do real quick. You're looking at this integral. There's the 1 over 4 pi epsilon naught that comes out. That's k. And then you've got dq over r squared. And you're doing this for this line of charge going B, A, and then up to this point here, C, or that's C, right? You're trying to sum up each of these tiny little bits of charge, dq, and you're trying to do that for some distance r away, where this, wherever you're at, like let's say you're right here, that is some distance x, this is some distance c. So if we think about dq, we know that q in general, if you wanted the entire charge here, q can be thought of as the density by some length, and that means dq is going to be some density times a tiny bit of length, like that. So what we kind of have initially is the k, the 1 over 4 pi epsilon naught, integral of lambda dx, and that lambda is going to come to the outside, as we see in the problem, over this r squared amount. And the r squared amount's where things start to get tricky, because in order to find that r squared amount, we have to say that r here, or rather r squared, is equal to, and if I take a look at this awesome triangle that we have built, we can say it's equal to x squared plus c squared, just like that. So we can call this right now lambda k, the 1 over 4 pi epsilon naught, integrate dx, and then x squared plus c squared. Now, and this goes from like negative b to a, because this is like the negative side, and then we're heading out to positive a. Now, if you look at this, we look at our problem here, you might be like, wait, that means x is wrong, because I have a 3/2 here. This can't be right. Well, this is in the horizontal direction and the vertical direction, which means that when we just found this integral right here, we were looking for the electric field. This all equals the electric field here. I don't want the electric field. I want the electric field that is occurring in just the x direction. And that means that whatever angle is down here, theta, is the same angle up here, theta. In order to find that, or if we're looking at the x component here, you want to take this amount and multiply it by the cosine of theta. Well, what is the cosine of theta? Well, you have it back here in this triangle again. Cosine of theta is an adjacent over a hypotenuse. So what you can say here is that cosine of theta is equal to x over, and then this is going to be x squared plus c squared to the 1/2 power. We took a square root here in order to get rid of that. So now when we go ahead and put this back in, we can say that E in the x direction, the horizontal component, is equal to lambda k, the 1/4 pi epsilon naught, integral minus b to positive a. And now what we have is x dx, because here is an x and then there's our dx, over, and then we've got x squared plus c squared to the first power, which is the same as the 2/2 power, and then times x squared plus c squared to the 1/2. So we're going to get x squared plus c squared to the 3/2 power, which that is what we have here in the horizontal component. So the horizontal component is good. That means the vertical component has to be bad. So the vertical component's wrong. What we see from the vertical component is the same kind of issues whenever we were looking at the x component. If we were to solve this, we are trying to sum up all of the charge, and the charge is going across here. The charge is going along the x-axis, but they're trying to integrate in the y direction, so that dy cannot be correct. So that's the first thing that's wrong there. Secondly, if you go through and you kind of work out that trig that we did, they don't have the 3/2 power here. They're missing that. So that's the other issue that pops up. They don't have the 3/2 power, and then they're integrating in the wrong direction. But that's how we can just talk about the integral that's wrong. You may have had to jot something down, just like we did, like, I gotta scramble, gotta do an integral, this is a pain. But in the end, they just want you to talk about it. So the things we can talk about are, they're integrating in the wrong direction. This dy should be a dx. And they're missing a 3/2 power down here in order to integrate that properly. So that right there, like, while that is all a classic AP Physics C mechanics problem with Gauss's law and integrals, we did a lot more just kind of explaining in this problem than actually trying to crush out the math. And that's what we're probably going to see this year due to the whole COVID-19 thing. So far, this video has been going on for about 13 minutes. This problem, you should have about 20 to 25 minutes on. So if we were able to get through it about this fast, then you should still have another 7, 8, 9 minutes to just start typing, because we talk a lot faster than we type. But you want to practice those typing games and get some quick fingers there, because you're going to have only a few minutes to kind of type all this out and make sure that you're on the right pace. So that's just one example. We'll be doing more examples of this kind of stuff as we go, but that's what you should be thinking about as you're looking at other free response questions. Start thinking about, how would I not math this out on pen and paper, but how would I kind of describe it to a reader that I know what I'm talking about, and you should believe I know what I'm talking about based on my description. So that's kind of how things have changed this year. Hope you got something out of that. Other than that, this problem's finished. Take it easy, check some more stuff out, check out the other videos, and have a good one. Adios.